こんにちは。定刻になりましたので、第283回定例オープンセミナーを始めたいと思います。本日の司会させていただきますのは、生存科学計算機実験分野の大村です。よろしくお願いします。I'd like to introduce today's speaker, Dr. Yikai Hsieh. Let me introduce her history of work experience and education. She has been with us as a project assistant professor last 2 years, and before that, she worked as a researcher, program-specific researcher, and research assistant. She has obtained a PhD at Kyoto University, engineering, faculty of engineering. And before that, she worked at Academia Sinica as a research assistant for 1.5 years. And before that, she worked she obtained Master of Science at the National Central University, Taiwan. She has been awarded the Young Scientist Award from the URSI, International Union of Radio Science. Today, she's going to talk about the research topics she has been working on, the Earth's radiation belt dynamics associated with Whistler mode chorus emissions. Okay, Dr. Hsieh, could you start your seminar?
Okay, thank you very much for introducing me. Okay, my name is Yikai Hsieh, and I'm from Taiwan, and I belong to the Laboratory of Computer Simulation for Humanospheric Science, RISH. And today my topic is about radiation belt dynamics. Especially, I want to talk about the wave-particle interaction inside the radiation belt between the Whistler mode chorus emission and electrons. Okay, as you can see, this is a picture from NASA. Here is our living Earth, and we have a high energetic particle region around the Earth, and this region is called radiation belt. Excuse me, can I go to next page? Oh, okay, sorry, this is my outline. So I will start from what is radiation belt. Okay, then the story starts from 1958. So how did people recognize there is a radiation belt and how they found it? Initially, by the theory, by the calculation, many scientists predict that the energetic particle should be trapped inside the Earth's magnetosphere. But they never found it because before 1958, there is no satellite to that area. Okay, this is a picture took after the successful orbiting of the Explorer-1 satellite. And this satellite is the very first American satellite. Then, why is it important? It's because this satellite found the radiation in the magnetosphere outside the Earth. Okay, and this is an important person, James A. Van Allen. The radiation belt is named by he. Then here, this have very simple design for Explorer-1. You have a Geiger counter attached to a tape recorder like this one. I cannot find a good photo for the Geiger counter on board the Explorer-1, but I only found this tape recorder. Then after Explorer-1, they record the radiations, and then a few months after the launch of Explorer-1, they launched Explorer-2, but unfortunately the launch failed. And after a few months, they launched the Explorer-3, and this one shows the data from Explorer-3. You can see, it counts the radiations, the high energy electrons like this. So this is the first, it's the first observation from the artificial satellite. So it's very important. It opens the satellite areas of space science. Okay, then here shows the structure of radiation belts. We have the Earth in the center, and you have outer radiation belt located between L equal to 4 to about L equal to 6. And then we have the inner radiation belt, which is much closer to the Earth. Then between the two belts, we have a slot. In this figure, you can also see they mentioned another things. For example, we have International Space Station here, and we have GPS Opter here, and we have geostationary orbiter around here. So these satellite orbiters will pass through the radiation belts. Then why it called radiation belts? Because it contains high energy particles. The upper panel shows the protons which energy greater than 10 MeV. So here, so many in the energetic protons remain in inner belt. And the lower panel shows the electrons with energy higher than 0.5 MeV. So they remain in the outer belt and inner belt. The source of these high energy particles are believed to have to be like a cosmic ray or from solar flare. Or some particles might be drained from the upper atmosphere. And you might have some local acceleration, local particle acceleration inside the radiation belt that contribute to the energetic particles. And why we say it is energetic? First, we can compare to the particles inside different area in the magnetosphere. So here shows the structure of magnetosphere. We have ring current, which also contains the relatively high particles. And the energy here is about few keV. And we have plasma sphere, which contains dense plasmas. And the plasma inside with energy about few eV. And outside the magnetosphere, we have solar wind area. And the energy of solar wind is about few keV. So compared to them, the NeV electron and protons, they have energy much higher than other areas. And if we check the velocity of these electrons in radiation belt, the particle velocity can be very close to the light speed. And in other area, it's much slower than the particle inside radiation belts. And these high speed radiation belt particles will hit or damage the satellites or other spacecrafts in the Earth, around the Earth. Here shows the relativistic electrons in the outer radiation belt. In this talk, I will focus on outer radiation belt electrons. So here shows the three characteristic periodic motion for about 1 MeV electrons near the geostationary orbit. Geostationary orbit is with a radii about 6.6 Earth radii. And then we have three kinds of motion. So first is driver motion. The second one is bounce motion. The third one is drift motion. It will drift around the Earth. The time scale are very different. So for one MeV electron, for one driver period, it's about 10 to -3 seconds. And for one bounce period, it's about 1 second. And for the drift motion, the particles requires about few minutes to drift around the Earth. And this figure shows the satellite observation of outer radiation belt. So this red part shows the very high energy flux in the outer radiation belt. So you can see the time scale is a year. Then you can find the radiation belt is not very spatial. So for outer radiation belt, it will swell and shrinks over time. It depends on the solar activities and geometric activities. And why we want to learn about the radiation belt is because understanding the radiation belt environment and its variability has extremely important practical applications in the areas of spacecraft operations, spacecraft and spacecraft system design and mission planning. And also, by learning the radiation belt, we can save the astronauts. Not only the Earth have radiation belts, the other planets also contains radiation belts around them. For example, you can see this is Jupiter. In Jupiter, we also have one radiation belt here. And for Saturn, we have several belts. Here it shows 3 belts there. So by studying the process of particle acceleration physics in the Earth's radiation belt, it can help us to know what's going on in other planets. So next, going to what is Whittemore chorus emissions. So generally, the basic characteristics is that Whittemore waves is electromagnetic waves with right-hand polarization. We can call it R-mode. It's an R-mode wave. You can see this figure. The wave is moving in this direction, and then the E field, electric field and magnetic field is rotating in the right-handed polarization. And the frequency range of the Whittemore waves is between the electron spectrum frequency and the square root of electron driver frequency times proton driver frequency. And this frequency range is right inside the frequencies here, our ear can hear it. So here shows 3 different kinds of Whittemore waves. First is Whistler. So first one is called Whistler. It's generated by lightning. Here shows the spectrum of Whistler. You can see the very clear falling tone. And please hear the sound of Whistler. Okay, so for Whistler, the frequency range is relatively lower than the other 2. Okay, and the second one is called Hsieh. And Hsieh is in this upper area. It looks like a structureless, but actually it has fine structure inside. Okay, and let's hear the voice of Hsieh. Well, you can hear like the 2 very clear sound that is by the chorus here, that is not Hsieh, but the other part are Hsieh. Let me start here. Oh, sorry. Okay, then the final one is chorus. You can leave it in chorus, also called chorus emission, because you have many consecutive emissions and one followed by another one. Okay, let's hear the voice of chorus. But please notice, even if we can hear these voices, actually in this space we cannot hear anything when the waves occurs, because the wave is not a longitudinal wave. The voice is generated by transfer the signal of waves into the voice signal. Okay. Where can we find the chorus waves? This figure shows the waves inside the magnetosphere, some important waves, and chorus are located around this area. We have sun here, and it's downside. We have dusk side and night side. In downside, we usually have more chorus occurrence rate. So the chorus here is also called down chorus. And because the voice here, this chorus voice, sounds very similar to the bird, bird singing in the morning. So this name, not only because of the location, but also because the feature of the voice. So here we have down chorus. Then why the occurrence rate is higher in the daytime? That is because in the figure it sketch the negative hard particle drift flow. We have if we have event that the hard particle injected from the tail side. Sorry, where is my pointer? Okay, we have particle inject here, and it will go through this path because the negative particles, electrons, move like this way. So in the downside, we will have higher occurrence rate of the wave because the wave is generated by these electrons. Okay, and let's go to the detailed feature of the chorus emissions. Usually we can find the range of chorus is 0.1 to 0.8 electron joule frequency. And we can find a gap at 0.5 electron joule frequency. So as this figure shows, we have a gap here. It's right at 0.5 electron joule frequency. Above the gap, we call the upper band chorus, and below the gap, it's called lower band chorus. And this figure is quite interesting because we can see different tendency of the frequency changing. For upper band chorus, the frequency is start from the lower part and then higher part. But for the lower band chorus, the higher frequency comes before the low frequency. So the tendency, the frequency sweep rate are in different aspects. And usually the source region of a chorus is near the geometric equator, or we can say it is at the place with minimum background magnetic field. And this slide shows the symplectic structure of chorus emissions. These are these are observation from varying probes. Okay, we can see a very clear chorus emissions here. But if we look closer into this emission, we can see the amplitude is not very stable. We have this up and down, up, down, up, down structure. And this is another observation. So for these emissions, still from the spectrum, we can see it's quite stable, but actually it's not. The amplitude is also up and down and up and down and up and down. This symplectic structure affects the wave particle interaction much. And why the wave particle interaction between Huysmans chorus emission and electron is important? That is because it can contribute to electron acceleration and the electron precipitation. And here also shows the observation. We have chorus events here. And after chorus, we can find a strong NeV electron enhancement. So we can sure that there are some relationship between the chorus and this enhancement. And also in precipitation part, the observation found chorus events, and we can see the fine rising tone here around this area. And then together with the chorus in the near Earth satellite, they detect the microburst, which means the loss of electrons. The electrons was lost into the ionosphere. So in this study, we are going to check what is the mechanism of this acceleration and precipitation. Okay, so next part is the Huysmans wave-particle interaction. So first, let me introduce what is spectrum resonance. So from this figure, we can see we have electrons rotating in the background magnetic field, and we have wave propagated from here, from right to left. And during the Doppler shift, if the rotation frequency of the electron and the rotation frequency of the wave are very similar, then the interaction happens. So here is the resonance condition. We have resonance velocity, which means the parallel velocity of electron. And this equation specifies that is the condition the particle sees the wave field rotation is exactly the same as the rotation frequency of the electron. And this gamma is the Lorentz factor. It comes from the very high energy electron. And then we have Lorentz force, F equal to this one, E plus V cross B. And if we only consider a purely parallel wave, and the purely parallel wave means the wave propagation is parallel to the background magnetic field, then in that sense, we will have electric field perpendicular to the background, and the perpendicular, perpendicular to the background, and is in the same plane of the electron rotation. So if we can find the electron in the rotation, in this position, moving to the downside, and the electric field is in the different direction, then the particle can gain the energy from the electric field during the rotation. And because the wave rotation is always in opposite side of the electron rotation, so this interaction is very effective. Then for the interactions, we can, So for wave-particle interaction, we can separate them into 3 different processes. So first one is called diffusion. We can check the electron pitch angle and kinetic energy of the particles. So under diffusion, the particle energy and electron pitch angle slightly shifted. And the second one is called nonlinear scattering. And in some paper or in some other study, they also call it phase function or dislocation. So under the spectrum resonance, the energy and electron pitch angle slightly become lower. The third one is called nonlinear trapping, and it's also called fast trapping. So under this process, the energy and electron pitch angle of a particle can be increased in a very short time period. And here we can see the generalized phase of a particle. The generalized phase is the angle, basically is the angle between the wave magnetic field and the particle perpendicular velocity. And then here shows the phase diagram. We have the generalized phase here and the velocity here. And here, the cross area shows the wave potential. If the particle is inside this wave potential, it was trapped. If the particle is outside the wave potential, then it goes through the nonlinear scattering process. And if there is no clear wave potential, the particle just go the diffusion process. Oh, sorry, here I forgot to talk about what is the equatorial pitch angle. So first, let me talk what is pitch angle. Pitch angle is the angle between the background magnetic field and the velocity, particle velocity. And then because the magnetic field strength changes, then we can convert a local equatorial pitch angle to equatorial pitch angle. It means when the particle moves to the equatorial region, what is the pitch angle at that position? So here is the formula. Considering the magnetic field at the equator, we can define an area which calls loss cone. If the particle inside the loss cone, then it cannot be trapped by the magnetic field. It will lost at a high latitude. So if a particle moves to the loss cone, we'll call the particle will lost from the magnetic field. And then my study focused on the differences between oblique Huysmans waves and parallel Huysmans waves. This figure shows we really found many oblique Huysmans chorus waves in observation. So this one shows the example of low band chorus. We have very clear structure of rising tone emission. Here this panel shows the wave normal angle. The wave normal angle is about 20 to 30 degrees. It's not parallel. And also for upper band chorus, we have a very clear structure of emissions. And again, the wave normal angle is about 20 to 30 degrees. And this figure shows statistic result of chorus wave normal angles of two different satellites. And this raised rectangle area shows the oblique events, and the other part are parallel or quasi-parallel events. So from these two studies, we can find in the magnetosphere, there are more oblique events than parallel events. Here shows the dispersion relation of two different kinds of chorus emissions, Huysmans wave emissions. So you can find for parallel waves, the dispersion relation is relatively easy, simple. It's a right-hand polarized dispersion relation. If we go to the oblique ones, we can find it's much more complicated. So therefore, we have already many studies work about parallel chorus wave particle interaction, but only a few studies focus on the oblique wave particle interaction. Yeah, this is one of the reasons, because the wave is much complicated than parallel ones. So if we see the wave field structure, we have wave propagation to this position. And for parallel waves, the wave field, E field or B field, just perpendicular to the background magnetic field. But for oblique waves, we have wave normal angle, so here, and E field and B field are not really lying on the perpendicular direction of background, and even not perpendicular to the wave propagation angle. Then, what's the difference between parallel and oblique wave particle interactions? Previously, we discussed about the saxon resonance, and we showed the resonance velocity. And here, for oblique wave particle interaction, we have this n number, which is harmonic number. The resonance condition is slightly difficult than the parallel one, because this n number, we have harmonic resonance. And this figure shows different resonances. So the first panel shows the interaction between electron and parallel waves. This figure is the trajectory in latitude and the velocity, parallel velocity, phase space. And with these resonance velocity curves, we can recognize the particle is undergoing which resonances. Then, for this case, we can find the we can find the particle only undergoes n equal 1 section resonance. But for oblique particle interaction, here we can find not only n equal 1, we can also find n equal 0 resonance and n equal 2 resonances. So it makes the resonance much complicated than the parallel wave particle interaction. Here shows the tendencies of the pitch angle scattering and energy changing under different resonances. Because the n equal 1 sectional resonance and the n equal 0 random resonance contribute to the most of the wave particle interaction. So here we just talk about these two resonances. Then, according to this figure, we have found if a particle undergoing nonlinear trapping via sectional resonance, the energy and pitch angle getting higher. If it is nonlinear trapping via lambda resonance, and the energy getting higher, but equatorial pitch angle getting smaller. If it is nonlinear scattering via sectional resonance, the energy and the equatorial pitch angle become smaller. If it is nonlinear scattering via lambda resonance, the equatorial pitch angle getting higher, but energy getting smaller. Okay, as shown in this figure. But here we have to be careful. The tendencies of the n smaller than 1, like n to -1, the tendency is the same as the lambda resonance. And the tendency of n greater than 1, it moves as the sectron frequency. Like here we have n equal 2. And for electrons at high equatorial pitch angle and high energy, the tendency of sectron resonance appears like a lambda resonance. This part should be very careful because it's different from the other energy and the kinetic energy and equatorial pitch angle position of the sectron resonance. So basically here we can check the acceleration is contributed by nonlinear trapping, and the precipitation of electron is contributed by both sectron resonance and the lambda resonance. Okay. Now I will talk about the formation process and loss processes of energetic electrons. I use numerical simulation to achieve our goals because the simulation is quite complicated, so I do not go into detail. I use a method called numerical Green's function. In this function, first I will set a wave model and perform test particle simulation based on the wave model, and then obtain the Green's function. And with the Green's function, we can do the convolution integral. With convolution integral, we can obtain the electron distribution function after interacting with many emissions. Of course, we have many emissions in an event. Okay. So here the most important things is a wave model. Here shows my wave profile in amplitude and frequency. So I have rising tone frequency and subpacket structure. And then I try 3 different cases with 3 different wave normal angle setting. So sorry, it was very small, but first I have a case 1, which is purely parallel case, and I have case 2, which is relativity oblique case, and case 3 is quite oblique case. And then in the test particle simulation, I will input a group of particles. And then after the particles interact with this wave, I will obtain the new distribution of these particles. And then I have the initial input particles in various kinetic energy and various equatorial pitch angle. Then we can do the convolution integral. So for the result, initially I will input the particle at 10 to 30 keV and then see what happens. Okay, here is the result. Okay, so we have parallel case and the relatively oblique case and the very oblique case. Okay, this is the animation. So first we can find a very, very effective acceleration in the parallel case. And then for the oblique case, the acceleration actually is faster within like 3 emissions. But then it slows down when the particle reaches 2 MeV. And the pitch angle scattering are very different from parallel case and the other 2 oblique case. We can find especially the particle acceleration very strong in here. But for oblique case, the pitch angle scattering, or we say the acceleration part is quite even in each equatorial pitch angle. Okay. So here shows some snapshot of the previous, animation. Okay. So here the magenta curve shows the electrons trapped in the magnetic field, and this dark green line shows the electron inside the loss cone, means the precipitation part. So initially, if we just have a few particles, we have few emissions, the acceleration for oblique with the mode waves is faster than parallel part. But as the emission increases, the parallel emissions can contribute to more energetic electrons here. So we have a small summary here for formation process. The formation process is contributed by nonlinear trapping, as I shown the previous slides. The tendency of the nonlinear trapping in both cyclone resonance and the Landau resonance contribute to the acceleration. And then the oblique cross emissions energize keV electrons to about 1 MeV rapidly within 3 emissions. They can accelerate to the MeV level. And this is much faster than the parallel cross acceleration. But after the particle reaches about 2 MeV, the acceleration slows down. And after long time evolutions, the parallel cross can contribute to higher electron acceleration. And then in the loss process, we find that the loss is directly contributed by nonlinear scattering. And this part I will explain later. And then the oblique cross emissions contribute to more precipitation, as we recognize by these dark green curves. Okay, so this slide shows the we analyze the acceleration via Landau and cyclone resonances. The energy gain of a trapped electron can easily be explained by these equations. It's delta H as the function of the mass and the energy gain and the interaction time and the homogeneity factor. Okay, now I plot it with different initial equatorial pitch angle and different kinetic energy. Then with 3 different minimum angle, we can find in parallel case, the energy gain can be very high here for the second resonance equal 1. But for oblique cases, this n equal 1 acceleration is especially in the high energy part is much weaker than the parallel case, like this one. And even if we still have like a very strong long-down resonance acceleration, long-down resonance energy gain here, but it suddenly become very weak when the electron energy exceed 2 or 3 MeV. So by this equation, we can check, yes, in the our simulation is consistent with our simulation for n equal 1 cyclone resonance, periparallel can contribute to more energy gain, especially in high equatorial pitch angle particles. And for for oblique chorus, the acceleration slows down after 2 MeV. And this figure shows the acceleration tendency for electrons undergo nonlinear trapping, only nonlinear trapping. Okay, so this arrow shows the tendencies. So we plot it as a function of electron pitch angle and kinetic energy. So first, for cyclotron resonance, we can find the tendency all moves the particle to higher equatorial pitch angle part. And for long-down resonance, the tendency is moved to lower equatorial pitch angle part, but it will stop at about 40 degrees. Now, below 40 or 30 degrees, we do not find any long-down resonance, nonlinear trapping by long-down resonance. Therefore, both cyclotron resonance and the long-down resonance cannot contribute to the precipitation of AV electron or even KV electrons. But we do find the precipitation which is higher, the precipitation is higher in the oblique case than in parallel case. This figure A shows the precipitation flux in our simulation. And I plotted in 2 different timing after the beginning of the simulation. With the energy, here is the precipitation flux. So in AV level, we have a higher precipitation in higher Wigner angle case. And here we compare like different amplitude case. So for case 3, is the previous case, the same as previous case 3, and case 4, the Wigner angle setting is the same as case 3, but we try a relatively small amplitude. And we can find the precipitation is much weaker than a large amplitude case. But still, if with a long time interaction, we can find some precipitation. So here comes the problem. Previously, we said nonlinear trapping by long-down resonance cannot contribute to the precipitation. Then why the oblique case can do contribute to more precipitation than parallel case? Okay. Then here, let's check the detailed trajectory of the particles of the electrons. So first one, we can find the nonlinear trapping by n equal 1 cyclone resonance here. So both the kinetic energy and the electron pitch angle getting higher. And then we have nonlinear scattering by n equal 1 cyclone resonance. Here, the particles move to the lowest cone during this process. And we have nonlinear trapping by n equal 0 long-down resonance here, and here. And actually, this one, we find the precipitation via long-down resonance, nonlinear trapping of long-down resonance, But this kind of case is very rare, and it also happens when the particle energy just in few keV. So for high energetic particle, it cannot happen. Okay, so again, so we verify that the main process that push the electron into lost cone is the nonlinear scattering by N=1 sectional resonance. Then, what is the reason oblique chorus contribute to more precipitation? Here we suggest two process. So two things we have to know. First is for nonlinear trapping via lambda resonance, it can move particles from high equatorial pitch angle to low equatorial pitch angle. And then the second thing is a particle can trapped by wave many times, and the equatorial pitch angle can getting lower and lower during different emissions. And finally, it can be pushed into the lost cone by nonlinear scattering via sectional resonance. Here shows the two-step precipitation processes. So first, we have a particle at a relatively high equatorial pitch angle here, and it interact with the emission via nonlinear trapping of nonlinear trapping of lambda resonance, and its energy becomes higher, and at the same time the equatorial pitch angle becomes smaller. And after the particle is trapped and bounced back and emit the second emissions, and this time it undergoes the nonlinear scattering of sectional resonance, and then in this process the particle is pushed into the lost cone. And finally, it precipitates in the upside hemisphere. So this process is the reason why oblique chorus contribute to more precipitation than parallel chorus. And then this is my summary. So first, we verify the process that Kuiper chorus emissions contribute to both acceleration and precipitation of the alteration belt electrons. And we use the Green's function and convolution integrals for oblique chorus and also parallel chorus. And we can see the evolution of electron flux in the alteration belt. And then we verify the two processes. So first, for formation process, oblique chorus contribute to the acceleration from keV to 1 MeV, and this acceleration is very fast. It can accelerate it from few keV to 1 MeV in only few seconds. And then for the long-term interactions, purely parallel contribute to more acceleration. It can accelerate electron to about 6 MeV. And in the loss process, oblique propagating chorus emissions cause more energetic electron precipitation than parallel chorus. And the reason is the combination of nonlinear trapping via lambda resonance and the nonlinear scattering via sectional resonance. Okay, it is all for my presentation, and thank you very much for your attention.